and also evening. Uh, Thank you very much for this support, sir. In India, the CPT use of CPT has been picking up. So I thought this is one of the right time to seek your inputs in the industry. So I requested you, and I'll just give all of you good morning. Peter Robertson, sir, doesn't need a special introduction. CPT and Professor Robertson goes synonymous in the geotechnical industry. Uh, Thank you, sir, and I'll be formally introducing Sir Professor. So, Professor Robertson has more than 5 decades of experience as an educator, researcher, consultant, and practitioner, specializing in the areas of in situ testing and soil investigation, earthquake design of geotechnical structures, and soil liquefaction. He is a co-author of the primary reference book on cone penetration testing as well as free CPT guide. It's one of the popular resources available in the industry on CPT. Professor Peter Robertson has also assisted in development of several inexpensive CPT-based interpretation software programs and has presented a series of free webinars in an effort to enhance education and practice, particularly advocating the CPT in soil investigation. He was the chair of expert panel to investigate failure of tailing dam failure in Brazil in 2019, one of the highly cited work. He continued to provide private consulting to a wide variety of clients and currently resides in Southern California. He is also a chief architect of the geologismic software, which is one of the very popular software being used in the industry, particularly use of CPT interpretation based software and liquefaction assessment based software. He's also one of the early person to promote and invent the seismic cone, which is very useful tool in measuring the shear wave velocity, which is one of the fundamental property in seismic ground response analysis. He's also, if you see, he's one of the CPT based liquefaction, one of the most popular stress based approach that you see in normally used in industry liquefaction assessment. He is the architect behind that. Thank you, sir. Thank you very much. And I would like to show this is my picture with you in 2014 at CPT when I first met you in Vegas paper. And this is me during the conference that time 2014. And thank you for your support to our work on CPT in landfills. We are the first to push the cone in landfills, and you are very supportive, particularly with the interpretation of CPT in landfills. And this work is published in one of the most highly impact factor journal, Waste Management. So these are the snapshot. Thank you so much, sir. You were really helpful. The night I write the email, I used to get the response the morning itself. So you're very prompt and very kind to me. Thank you so much.
You're welcome.
Over to you, Professor.
Okay, I'll share my screen. Hopefully it will work. I think you can see my screen now.
Yes. Yes, sir.
Correct? Good.
Yes, sir.
Good. Okay. Let's just minimize this. Oh, disappeared again. I think I clicked the wrong button. It disappeared. I'm not sure where it went. I'm not used to using Zoom. I'll stop sharing and then reshare. There you go. There it is. Okay, well, it's nice to be with you this morning. The goal of today really is to recognize that the CPT has been around for over 50 years. And so I thought I would summarize the developments in that 50 years and illustrate the sort of applications that you can use it for, both for geotechnical and geoenvironmental. I'll just touch on geoenvironmental very quickly. Oh dear. Just to go forward, here we go. So history. It was first developed in the 1930s. It was first developed as a mechanical device. So it was basically a rod with a conical tip, and it was pushed into the ground. and the force to push it in was measured at the ground surface. And you see this very old photograph. But in the 60s, that's when the first electric cone got developed. It was actually first built by Fugro, and that's when it took on the shape that we know it is today. So it's 10 square centimeters in cross-sectional area, which is about 37 millimeters in diameter. And it has a conical tip with a load cell and a sleeve with a load cell. So it would measure tip and sleeve where you pushed it into the ground. And then in the 70s, it was really took off. It was the primary device for offshore investigations, especially in the North Sea and the Gulf of Mexico. And then in the 2000s, that's when it became digital. The cones all went digital. The data was digital, and hence it was easier to process the data. And that's when we saw software development and making life much easier to use this data because you collect a lot of data with the cone. Typically, you're collecting data every 1 or 2 centimeters, and there's a minimum of 3 channels of data, which is the tip, the sleeve, and the pore pressure. So you get thousands of data points. So you get a very detailed profile, but it's a lot of data to process. And nowadays, with the digital data and software, it's a lot easier than it was 50 years ago. So let's look at the growth of CPT. It, of course, really developed in the late 60s, early 70s, and it was primarily in the Netherlands and Europe and a little bit in America. It was offshore in the Gulf of Mexico. And then in the 80s and 90s, it started to expand quite rapidly. And now today, it's pretty well worldwide. Um, I've just identified that in Russia, they do have an electric cone. It's not exactly the same as the international one. China likewise had their own cone design, but they've now switched over to the international one. So I really should be putting a big yellow area in China as well. So the evolution of the cones in the early days, when I first started cone testing, it was analog data and it went to a chart recorder. So the data was processed onto a piece of paper. And then when you needed to make calculations, you had to process it by hand, which was very time consuming. And then we started to digitize the charts, but it was very time consuming to digitize. And then in the late 90s and early 2000s, the cones went digital. So you had little microprocessors down in the cone, and the data was digitized and then transmitted up the cable in a digital format, and it would go to a computer. And in fact, in the early days, the computers didn't have much memory storage, and so typically you collected data every 5 centimeters because we just didn't have enough data storage to collect all the data. But now memory, of course, in computers is ubiquitous and it's relatively inexpensive. So most computers now have terabytes of data storage. And so storing the amount of data is not so much of a problem. And so it's quite common now to collect data every 1 centimeter. And over the years, there's been a push to make them wireless, although in reality, the wireless ones have not become as popular. And so they still tend to have a cable connected to the cone that travels up the inside of the push rods and goes to a data acquisition system at the surface. And that's because with digital data, you can measure multiple channels and have the data transmitted very rapidly up the cable. When you go wireless, it's a little bit more complex to have multiple channels of data. But in the future, it probably will go completely wireless. But currently, it generally still is a cone with a cable. So this is what the cones look like. And the first one on the left is a miniature cone of only 2 square centimeters. The second one is a 10 square centimeter cone, and that's the sort of the international standard. Let me get a laser pointer here. No, that's not going to cut it, is it? Forgotten how to, there it is, laser pointer. There, yeah. So the second one is the 10 square centimeter, and that was the most common for many years. But in about the 2000s, people started to realize that a 15 square centimeter cone was very useful to push. It was a little bit bigger, but it was dimensionally equivalent. You know, as the diameter got a little bit bigger, it went to 44 millimeters. The sleeve got a bit longer so that the length to diameter ratio of the sleeve stayed the same. The 15 square centimeter is a little bit more robust, easier to put in the electronics, but also it's easier to push into the ground. Because when you push the standard 10 square centimeter cone, you're typically pushing it in the ground with push rods that are also 10 square centimeters. And so if you were to just push that system into the ground, you would develop a lot of rod friction, and all of your push capacity would be consumed by the rod friction, and you would have limited depth capability. And so in the early days, it was very common to put a bump in the rods about a meter behind the cone. And that bump was called a friction reducer, and it was designed to push the soil away from the rods so that you would have less rod friction and you could push the cone deeper. And so when you have a 15 square centimeter cone, you still push it with 10 square centimeter rods. So it actually takes less force to push the 15 square centimeter cone in because it basically already has a built-in friction reducer. So it works out that it's actually easier to push the 15 square centimeter cone. And then in some parts of the world where there are gravelly soils, people have played around with a 40 square centimeter cone, as you can see on the right, designed to push into gravelly soils. But actually the 15 square centimeter cone is pretty good for most sandy gravels. But if it's really coarse gravel, you might need to go to a bigger one. But of course, then the push force gets bigger and you have to have a fairly big piece of equipment to push it. So the 10 and 15 square centimeter are now the most popular. They're accepted by nearly all the international standards. So it's not just the 10, the 15 square centimeter is also accepted as a standardized cone. And the mini cones are popular either for laboratory work or for very shallow investigations, such as is sometimes used in the offshore industry. So in general, 10 and 15 square centimeter cones, but the trend is moving towards 15 square centimeter cones. And when we first got into cone testing, we realized that when you lowered the cone in water, the tip resistance should measure the water pressure, but it was always reading less than the water pressure. Now, in the offshore industry, they got around that problem because they would zero the cone at the mud line. So they would sort of ignore the water above, and everything would start at zero at the mud line. But when you're pushing the cones into saturated soil, there's obviously water in the soil, so the water is surrounding the cone. And what happens is the water gets in the little gap that's behind the tip and in front of the sleeve. So the O-ring seal that keeps the water out is behind the tip. And so the water actually gets in on that shoulder of the cone. And so when I was working with Professor Campanella, we came up with a small correction that said the actual corrected tip resistance is the measured tip resistance, which is the load divided by the gross cross-sectional area. And you made this small correction that was the water pressure on that shoulder into 1 minus the net area ratio. And the net area ratio, physically, it's the ratio of the area of the load cell, sorry, the area of the tip divided, sorry, the area of the load cell divided by the area of the tip, which for most modern day cones is around 80%. Now, in the early days, it was as low as 60%, but now most cones have quite large load cells, and so it takes up a bigger portion of the total cone. So the net area ratio is typically 80%. So 1 minus 80% is 20%. So you make a small correction of 20% of the water pressure. Now in sands, the tip resistance is very large and the water pressure is usually low because in sands it's a drained penetration, so there's no excess pore pressure. So maybe 1 or 2 atmospheres of water pressure, but the tip resistance might be 100 atmospheres. So the correction in sands is essentially insignificant. So quite often when you see interpretation of CPT data in sands, you'll see QC written where it really wants it to be QT, but they're essentially exactly the same. But in soft clays, the tip resistance can be quite small, maybe only 4 or 5 atmospheres. And the pore pressure now, because it's a soft clay, you generate large excess pore pressures. So the pore pressures can be 80% of the measured cone resistance. So you end up making a correction of 20% on that. So it has about a 10 to 15% correction on the tip resistance in very soft clays. So that's about the maximum of the correction. It's about a 10 to 15% correction in very soft clays. And it's pretty ubiquitous now. It's required in all the standards. So all the standards require you to calculate QT, which means you need the water pressure. Now, if you don't have the water pressure, the error is generally pretty small. Maybe a 10% error in very soft clays. In stiff clays, it's insignificant, and in sands, it's insignificant. So it's not a big correction, and it's pretty standard. And in theory, there's a similar correction for the sleeve. In the early days, the sleeve was designed to latch onto the load cell. And so the cross-sectional area of the top of the sleeve would be different than the bottom of the sleeve. And so when you immersed it in water, you'd have equal water pressure, but because the cross-sectional areas were different, it would induce a small force. And so you would actually measure a small sleeve friction when you were pushing the cone in water. And so to get around that problem, virtually all cones now come with equal end area sleeves so that they have equal end areas. So when you lower them in water, they don't generate any sleeve resistance. So you measure zero sleeve resistance when you're in water. So those are the only two main things to understand about any sort of corrections for cone data, is this correction to the total tip stress QT, and to make sure that the cone has equal end area friction sleeves, which is pretty well standard in all manufacturers, and it's required in all standards. So in the early days, cones generally were designed to have a high capacity. So they were designed that if you were going to push through very hard ground, you needed to have a cone that might have a tip resistance capacity of up to 100 megapascals. Now that's 1,000 atmospheres of stress. That's a very big number. So with these high capacity cones, you can actually push them through a typical asphalt roadway. So if you've got enough reaction force, so if you have a reaction force of 20 tons, you can push these cones through pretty strong material near the surface. But if you're pushing into very soft ground, to have improved accuracy, you want to use a cone of a lower capacity. And now they make cones down to as low as 3 megapascals on the tip. So there's a wide range of cones of different capacities, which means they have different levels of accuracy. And generally what happens is, if you're not quite sure how hard the ground is, you typically use a high capacity cone to start with. And if the geology says that, well, there could be some soft ground, and so you use a high capacity one to start, and if it confirms, yes, the ground is very soft, then sometimes people will switch over to a lower capacity cone so that you have improved accuracy. But in general, the quality of the strain gauges is so good now that even the high capacity cones have remarkably good accuracy in softer soils. But conceptually, if you want improved accuracy, you should use a cone of slightly lower maximum capacity. In terms of sensors, over the last 50 years, lots of sensors have been added. The first one was a simple inclinometer. That was so that you could check if the cone was remaining vertical while you pushed it. Because when you may start off vertical, but the cone will have a tendency to drift slightly off of vertical. And a lot of systems will measure that drift, and they'll often have a warning that if you get over more than 5 or 6 degrees, that a warning that the inclination is beginning to pick up a little bit. And for many operators, if you hit something like a boulder and the cone suddenly gets deflected, then a sudden change in inclination is a warning that you may in fact damage a rod, and you may break a rod. And so if there's a sudden change in inclination, then typically you stop and pull out and then move over a short distance and go back down again to avoid hitting whatever that hard object was. And then temperature sensors were added. The awareness that although the strain gauges are very accurate inside the cone, they are slightly temperature sensitive. And so I lived in Canada for a long time, and so although the air temperature might be quite warm, the ground temperature is usually quite cool. And so in Canada, of course, the water temperature can be very cool. And so it might be a hot day with 30 degrees air temperature, but when you push it into the ground, it drops to 10 degrees. And so that temperature shift can affect the strain gauges. But nearly all cones now have a simple temperature sensor on the strain gauge, and they're all temperature compensated. So pretty now standardized that they're temperature compensated. And then over the years, things like measuring the electrical conductivity or resistivity has been added, measuring passive natural gamma. Of course, video cameras have been added to the cone so you can look at the soil as it's going through. That's never really caught on very much. And that's partly because if you go out and spend 8 hours a day pushing CPT, it's pretty boring watching 8 hours of video of watching the soil going by. But it has found some applications in special situations such as environmental, where people actually want to see what the contaminant looks like, if it's visually possible, or if you've got a highly interbedded deposit and you wanted to actually see the bedding. But generally, it hasn't become that popular. In Europe, magnetometers have been added to detect metal. And in fact, surprisingly, in Europe, it's now quite common to use the cone with a magnetometer to detect unexploded bombs from World War II. And so you push rather slowly, and you detect if you're approaching something that has a lot of metal in it. And of course, if it detects that you're approaching something with a lot of metal, you stop, and then you determine that, well, there's something with a lot of metal there, and it could be a buried bomb. And then we'll talk a little bit about a hydraulic profiling tool for environmental purposes, and recently things like magnetic resonance to measure water content. And of course, on the right-hand side, in the 70s, pore pressure measurements were added. And then in the 80s, we added shear wave velocity and then P wave velocity. And then for environmental, there was dielectric, active gamma, which never caught on, acoustic, listening to the sound, and then sampling, both vapor sampling and water sampling, etc. So the number of sensors that can be added to cones has increased enormously. Most of them have come out of the geophysical world, and many of the applications have been in the environmental. The ones for geotechnical are primarily measuring water pressure and seismic. Those are the most popular additions for geotechnical applications. When it comes to the cones, in the early 70s, they measured just tip and sleeve, like the one on the left here. And then in the 70s, pore pressure was added. And in the very early days, it was a sensor added to the face of the cone. And then people realized, well, maybe it's better if we put it on the shoulder for two reasons. The one on the face typically would get damaged very easily, whereas the one on the shoulder was easier to saturate and it didn't get damaged. And it gave the pore pressure measurement that you needed to make that unequal end area correction on the tip. So hence you needed it to make that correction. So the most common one is where you measure it on the shoulder, sometimes referred to as the U2 location. So U1 is on the face, U2 is on the shoulder, and some people have put a U3 behind the sleeve, but that didn't become very popular, so U2 tends to dominate. And most cones are designed that you can unscrew the conical tip and replace it with a face U1 pressure sensor if you want. So you can measure either U1 or U2 with the same cone. It doesn't need any special changes. So U2 has become now the most common location. And as I say, in the early 80s, we added geophones into the cone so that you can measure shear wave velocity. And so the attraction of shear wave velocity is you have a device that you're going to push in. You're going to measure this tip resistance, which is the load on the tip divided by the cross-sectional area. And of course, you measure the sleeve friction, which is the load as the soil passes the sleeve divided by the surface area. So that gives you the frictional resistance in units of stress. And then, of course, you've got the water pressure. So you've got tip, sleeve, and pore pressure all in units of stress. And then, of course, there's an inclinometer, and then a geophone was added so that you can measure shear wave velocity. So you get up to 7 measurements. You get the tip, sleeve, pore pressure, shear wave velocity, and of course now we can also get P wave velocity, and you get inclination. And when you're pushing through clays and you develop large excess pore pressures, you can stop and let those pore pressures dissipate. And if you record the rate of dissipation, a measure of how rapidly it's dissipating is you record the time it takes to dissipate 50% of the excess pore pressure, and that's referred to as T50. I'll mention it again a little bit later. And that is a measure of the permeability because it tells you how rapidly the pore pressures are dissipating. And then when they dissipate to equilibrium, you get the equilibrium pore pressure, which is often referred to as U0. So you get 7 measurements. And you get that in a very efficient, cost-effective manner. So for example, a 30-meter CPT sounding, if you're just doing tip, sleeve, and pore pressure, then it would take less than an hour to do that 30 meters. If you measured shear wave velocity every meter and you did 2 or 3 dissipations, then maybe the test would take 2 hours. So you can do a 30-meter sounding, get all these 7 measurements, and it takes only 2 hours or so to do, depending on how many dissipation tests you do and how long the dissipations are. And when it comes to dissipation tests, if you're primarily interested in the groundwater condition, so you want to know what U0 is, so you want to get the piezometric profile to determine the ground surface and determine whether or not the piezometric profile is in fact hydrostatic, or if it's non-hydrostatic, there might be vertical flow. Then generally people stop in the sand layers, because when you stop in the sand layers, either the penetration is completely drained to start with, and you're already measuring equilibrium pore pressures, or the dissipation is very rapid, and after maybe only 30 seconds or less than a minute, you've come to equilibrium and you get the equilibrium pore pressure to know what the piezometric profile is. So if you're interested in groundwater, you stop in the sand layers. And if you're worried about rate of consolidation of clay layers, then you can stop and do a dissipation in the clay layers, and that will give you T50, which you can then determine coefficient of consolidation and permeability to determine the rate of consolidation. Now, over the years, a number of standards have been developed. A lot of national standards exist. So here in North America, there's the American Standard of Testing, ASTM, and that gets updated about every 5 years. And there are a number of European standards, and that got upgraded to an international standard, an ISO standard, and that was recently updated in 2022. So ISO has updated it, and that now has identified different classes of cones. So basically based on the accuracy level that a cone can have. And so I think it's sort of 1, 2, 3, and 4. So if you're going to push into very soft soils, you could use a low capacity cone that has very high level of accuracy in measurements. And if you're pushing into a wide range of soils, including dense soils, then you can use a sort of a lower class cone that doesn't quite have the same accuracy in the softer soils, but is perfectly adequate in the harder soils. And then they identify test categories, A, B, C, and D, and that would be based on project requirements, and it combines the class of the penetrometer with the test procedure. So it's a combination of the type of cone, what accuracy the cone itself has, and then the test procedures to make sure you can get the right class of cone data. So it's quite comprehensive. The biggest thing that comes out of it is something we developed almost 50 years ago, was the importance of taking zero load readings before and after every sounding. So before you start a sounding, you take a zero load reading on the tip, sleeve, and pore pressure. And so that tells you the baseline that everything is going to be referenced to. And at the end of the test, when you pull the cone out, you wipe the dirt off and you take another set of zero load readings. So you have a pre and post zero load readings. And if it was a perfect world, they would be identical. But it's not a perfect world. Soil gets into the seals of the cones a little bit. And so there might be a slight shift in the zero load readings. And that's used as a measure of the quality of the cone data, that zero load shift should be very small relative to the readings you were taking. So these standards go through all those details. And if you're specifying that cone testing should be done, then you should specify the standard at which it should be done. So if you're a consultant and you want a contractor to do CPT, then you should say that it should be done according to some certain standard, whether or not there's an Indian standard or whether or not you want it done to the ISO standard, or even whether or not you want it done to ASTM. But at least that establishes a set of rules, and the contractor must follow those rules. And if you go out and supervise them, then the person you send out should have read the standard and then check that they are, in fact, following the procedures described in the standard. When it comes to pushing equipment, of course, in the early days, it was often very small portable equipment, and that now varies enormously around the world. There's a very wide range of equipment. So there's two elements of pushing equipment. One is the capability of the hydraulic pistons. How hard can they push? And it's quite common now to have 20-ton hydraulic pistons. So in the bottom right-hand corner, you can see a fairly two large hydraulic pistons that will allow you to push 20 tons. And then the next thing is to make sure you can actually generate a reaction force of 20 tons. So these smaller pieces of equipment, they get their reaction force typically from anchors. And if you look carefully, you can see that most of these are anchored down. The only one that's not anchored is this yellow one at the top. But if you look carefully, they all have a pair of anchors that they anchor the rig to the ground and then react up against the anchors, and then you can push with full 20 tons, even though the portable equipment weighs a lot less than that. So if you've got difficult locations to get into, then these smaller pieces of equipment have become very popular. And of course, they're relatively inexpensive to purchase. So they're also popular for companies that are first getting into CPT. But if you want high efficiency and you live in an urban area, then these trucks have become very popular because the trucks weigh 25 tons and you push from the center of gravity, so you don't need to anchor them down. And they have hydraulic jacks. In the middle, you can see the track-mounted unit is up on its jacks. And on the right, this combination of a track unit and wheeled unit, it's up on the tracks, which lifts the vehicle up and creates the full reaction force. So these are very efficient. So here in California, these trucks and track-mounted units are very popular because it's an urbanized area and the roads are quite large here. And so they drive these big vehicles around, and they're very comfortable inside. They're air conditioned, and they've got all the equipment you need, and they're highly efficient. So you can do 200 to 300 meters of CPT in a day under the right conditions. So you can collect a lot of CPT data in a day with these trucks. But there's also where you can take an existing drill rig and modify it to push CPT. So these are examples here. And then in recent years, sonic drilling is becoming very popular. So one of the companies in the Netherlands that makes sonic drilling realized is that it would be nice to add CPT to a sonic drill. And so they built a little hydraulic ram set that would fit in the chucks of the sonic rig. And you could do a static CPT to whatever depth you're able to push in. And then after you've pushed the CPT, you can then swing it out of the way, and then you could do sonic drilling down adjacent to or over the top of where you just push the CPT. And then they also hit on the idea that if you slim down the electronics in the cone so that they weren't so sensitive, that you could actually push it directly with the drill head of the sonic rig, turn the vibration off. But if you hit a hard layer, like a gravel layer or a very hard layer, you could turn the vibration back on again, vibrate the cone through the hard layer, and then once you got through the hard layer, turn the vibration off, and then carry on with a static push. So this is now becoming quite popular in regions where you've got complex ground conditions and where sonic drilling is very popular. And the reason sonic drilling has becoming popular is it gives you a continuous core that you can look at. Now, when it comes to looking at the soil, I said that people have added cameras, which is a bit cumbersome for CPT, but the Dutch, for a number of years, have developed simple little push-in samplers that allow you to get a soil sample using CPT pushing equipment. And so what's common practice now is you would push the cone to whatever depth you required for the project, and then you would pull the cone out, you would move over about a meter, and then you would go back down with a sampler, which basically looks like a cone, but it's got a sample tube inside, and you would go to a selected depth based on the cone profile. So you would look at the cone profile, identify the layer that you wanted to sample, move over, go down, go to that depth, pull back on the sampler to open it up, and then push to take the sampler. So the one on the left you can see is referred to as a Mostap sampler, which is a common type of sampler coming out of the Netherlands. And then the one in the middle here is one that's popular here in California. It's very simple. So it's a very simple device. You push it down, you pull back to open up the sample tube, and then it locks into place, and you push down and you get a sample. Both of them, typically the sample varies from about 25 millimeters up to about 50 millimeters, but can go as large as 75 millimeters in soft soils. And then in recent years, people have played around with using CPT equipment to push in long, thin-walled, undisturbed samplers. So they're pushed closed-ended, but they're thin-walled, but they're very long. So they're about a meter long. And so they're designed to push into very soft soils. They were originally designed to push into mine tailings, soft mine tailings. And so you'd push it to the required depth, and then you would pull back. It would be like a fixed piston sampler. No, you wouldn't pull back. You push it to the required depth, lock the piston, and then push the sampler about a meter. So it would take you past the zone of disturbance. So that if in soft soils, the zone of disturbance is maybe 1 or 2 diameters of the sampler, push closed-ended. And so if it's 75 millimeters, then about 150 millimeters would be disturbed. But if you take a meter-long sample, then the lower half of the sample is going to be in undisturbed soil. So people have had very good success of this, and it's become quite popular. So with CPT equipment, you can just push the cone, collect all the data, and you can also get samples as well. But instead of taking samples at standard depth intervals, like every 5 meters or whatever is typical practice, here in North America, it'd be 1.5 meters. With the cone, of course, you push the cone first, you get the profile, and then based on the profile, you decide which of the layers that are most important that you need to sample. Depends on the project. If it's liquefaction, you might be interested in sampling the silty sands. And if it's clay, you want to sample the softer, weaker clays that would be influencing the design of whatever the project was. Now, when it comes to pushing, in the early days, the push rods were all 1 meter long. And so you would push a meter, there would be a short pause while you added the next rod. The pause would be 10, 15 seconds, and then you'd carry on pushing. But in the offshore industry, there's been a move to do truly continuous pushing. So in the offshore, they have seabed devices that would have rollers, and you would pre-thread the rods, and you would continuously push the cone, and there would be no pause. And so various manufacturers have developed onshore devices. This is from Vandenberg in the Netherlands. And so it's got a roll of sort of short tubes. Rather than be a meter long, I think they're 0.5 meter long. And as they coil on and come down, they have a single twist to put them into place. So it's all automated. And so you get this continuous push with a double set of hydraulic rams. And so you don't have to pause. You just keep on pushing continuously. Of course, if you're going to do seismic, you need to pause to measure shear wave velocity. And while you're measuring shear wave velocity, you do a dissipation test. So usually the rods are not that much of a problem. It's actually quite convenient to have this ability to stop and measure shear wave velocity. So when we first started measuring shear wave velocities, since the rods are 1 meter long, we would typically measure shear wave velocities every 1 meter. It was a very convenient thing to do. And of course, you're also collecting dissipation data every 1 meter. And in the offshore industry, they developed these coiled tubing units. So with a miniature cone, a 5 square centimeter cone with a coiled tubing, and then as it's pushed into the ground, the coiled tubing gets straightened and the cone goes in straight. And then when you retract it, the tubing coils back up again. And that's become relatively popular offshore, less so onshore for various reasons. Now, when it comes to interpretation, over the last 50 years, a lot of developments have been made in interpretation. Initially, mostly laboratory work, where people were using full-size cones in large calibration chambers. Here, there's a picture of a large calibration chamber. This is the one from Oxford. And people looked at the correlation of relative density and friction angle in sands with these big chambers. And then people said, well, you could build smaller chambers for clay. And then they realized, well, we could use smaller cones and smaller chambers. So now there are miniature cones pushed into sort of oversized triaxial samples that are clay to get experimental data. But that work's been going on for 50 years. Most of it's been exhausted now. People have tested most types of soils under all different types of conditions. And so then it moved on to experimental test sites where various universities or research institutes like NGI in Norway, they would locate sites that they would study carefully. They would do lots of testing. They would drill, take samples, do lots of lab testing. And sometimes they would also do loading. Like here, this is a tailings facility there where they're building some test pads on top of the tailings to look to see how much the tailings settle and how much they improve in strength as they consolidate. So lots of test sites, as I say, university, national research site, project sites. And this has the advantage it's using natural soils, not sort of ideal soils in the laboratory. They've got variable stress history. They've got natural site variability, generally relatively shallow, although this one for this tailings dam, the tailings was 100 meters thick. So, and these pads extended 30 meters in thickness. So that's pretty large scale testing. But of course, over the years, people have done full-scale power load tests, etc. There's been a range of testing. There's also been big developments in numerical analysis. So in the early days, it was sort of simplified analysis like bearing capacity theory. And then it moved on to numerical analysis with things like finite element or finite displacement. And then people have also recently been done discrete element modeling. So lots of advances made in numerical modeling too. And also, there's lots of case histories. So in terms of liquefaction world, when Christchurch experienced 4 rather large earthquakes over a little over a 1 year time period, and there was lots of liquefaction, lots of damage. And then afterwards, the government realized that they needed to evaluate all of these sites to determine whether or not buildings could be built on these sites that had suffered liquefaction. So now it's over 30,000 CPTs have been done in Christchurch. So there's a huge database being collected. And of course, tailings dams are collecting thousands of CPTs around the world, as well as regional studies for cities looking at sort of regional liquefaction issues. So there's huge amounts of case history data being collected now and large volumes, like 30,000 from Christchurch alone. So we're dealing with big data and big data interpretation. Now, all of this has meant that you can do a very wide range of interpretation, and it's that although they're mostly seen as empirical, in reality they're semi-empirical. So what they're done is they're based on some theoretical basis, and then they're supported by laboratory as well as field trials. So they've been adjusted using theory as their basis. And so, you've got the tip, and So you've got the cone and you've got basic measurements of tip, the sleeve and pore pressure and maybe shear wave velocity. And of course, you can determine the state of the soil. So the relative density or the state parameter of sands or the OCR of a clay. And then you can get the strength of the soil, either the frictional strength or the undrained strength, both peak and remolded. You can get the stiffness of the soil, the Young's modulus, the shear modulus. And of course, you can get consolidation parameters, the pre-consolidation pressure, the compression index, as well as the coefficient of consolidation from dissipation test. And you get the in situ drainage conditions, whether or not the cone is being pushed in drained or it's undrained in a clay or partially drained. So you can determine all of those things. And of course, you can get the soil profile, which is still one of the most popular things that comes out of CPT is actually what is the profile of the ground. Where are the clays, where are the sands, and are they clay and are they sand, etc. Now, in the mid 80s, Professor Roth, when he gave his ranking lecture, he said that when you process cone data, you ideally should normalize the data because, of course, we know that when you push the cone in, it's influenced by the strength and stiffness of the soil. And as you go deeper and the overburden pressure gets higher, then of course the soil gets stronger and stiffer. So the cone resistance gets bigger the deeper you go. And so if you want to interpret the data, ideally you want to normalize out the effect of the overburden pressure. And so Roth said, well, ideally the best way to do that is you take the corrected tip resistance QT, you subtract the total overburden and divide it by the effective overburden pressure. And in a clay, in a normally consolidated clay, the tip resistance basically increases linearly with effective overburden pressure. And so if you normalize it, then the normalized cone resistance in a normally consolidated clay would stay constant. And so the normalized cone resistance is a measure of OCR. So if it's constant and it has a value of about 3 or 4, then it's normally consolidated. And as that normalized cone resistance gets higher, that means the OCR is getting higher in the clay. And of course, if the OCR is getting higher, that means it's getting stiffer and the pre-consolidation pressure is getting higher. And all of those things you can estimate from the cone data. And then in about 2009, actually it was a little bit earlier than that, but this is how I eventually finalized it. We recognized that when you push the cone into sands at a constant relative density, the cone doesn't increase linearly in depth, it increases non-linearly with depth. And so it's pretty now recognized that the cone resistance varies non-linearly in soils that are not clay. And so I came up with this expression that said you've got the net cone resistance divided by atmospheric pressure, and then atmospheric pressure divided by the effective overburden pressure to the power n. And if n is 1, like a soft clay, it goes back to Roth's original version. But in sands, n can typically be around 0.5. So depending on how dense the sand is, depends what that stress exponent is. So if it's very dense, it can be 0.4, and if it's quite loose, it can be around 0.7. And if it's silty sand, it's around 0.7, 0.8. So n varies as a function of soil type and density as well as stress level. So I came up with a little way to iterate on what n is. So what you would do is you would assume n was equal to 1, you calculate the normalized cone resistance, go into the soil behavior type chart, which I'll show you a little bit later, and then quickly iterate to get the correct n value for the correct normalization. And then that's become quite popular and it's pretty standard. So let's talk about interpreting soil type. So in the Netherlands, when they first did mechanical CPT and then started to do electric TPT, they had this sort of chart that said, well, if you looked at cone resistance against sleeve friction, then depending on the slope of the relationship was whether or not it was sand. So if you had a high tip resistance, it was typically sand. And if you had a low tip resistance for the same sleeve friction, then it was typically clay. And then in the 80s, we sort of said, well, the slope of this line is actually the friction ratio. So the friction ratio is the sleeve friction divided by the tip in units of stress as a percent. So it's the sleeve resistance divided by the tip multiplied by 100. And so that led to the development of this sort of well-known soil behavior type chart, which has got cone resistance on the vertical axis, which in the early days was just cone resistance. And then we realized, well, it should be normalized cone resistance. And then on the horizontal axis was this friction ratio. And friction ratio would vary typically from around 0.1 to as much as 10. Sometimes it's slightly over 10, but generally it fits within this range. So nearly all soils fit within this range. And we know that sands tend to have a high tip resistance and a low friction ratio, and clays tend to have a low tip resistance and high friction ratio, at least normally consolidated clays. The stiffer the clay, the higher the tip resistance gets. So these charts have been around quite a while. And in the early 90s, that's when people started to realize that, well, these boundaries between the different soil types are roughly concentric circles. So Jeffries and Davies in Vancouver said, well, why don't we look at the radius of these concentric circles, which is a combination of Q and F, so combination of the normalized cone resistance, the normalized friction ratio, and it would tell you roughly where on the chart you were. Since most of the data fits down the middle of the chart, then if this soil behavior type index IC is small, you're up in the sand region, and if it's large, you're down in the clay region. So IC would typically vary from about 1 to 4. And so if it was between 1 and 2, you were in sand, and if it was greater than 3, you were in a clay region. So it was a very simple way of identifying what type of soil it was. And it also turned out that many of the correlations, of course, also depend on soil type. So this IC has become very popular as a way of modifying correlations as a function of soil type. So a lot of correlations have IC built into it as a way of automatically varying the correlation as a function of soil type. And in the early days, everything was done in black and white, but then color printers became more popular. And so then it became popular to color code the charts. So the sands were typically orange or brown. The clay was typically blue, partly because of Boston blue clay. And red was considered a sensitive fine-grained soil. So red is a warning to say this material could be sensitive. And gray was given to sort of very stiff, almost soft rocks. So if it plotted way up in the right-hand corner, it could be a soft rock. And green was for silts. And so it was a nice way of visually sort of seeing the color. So now with software, you get plots of like the normalized tip resistance, and then taking the color from the soil behavior type chart and putting it underneath the tip resistance. So you can visually sort of see that when the tip resistance is large, it's a sand, and when it's low, it's a clay. So various ways of seeing. So the middle plot is IC, which also you can see goes from sand to clay. And then the one on the right is basically the soil behavior type, both in terms of its number and its color and the words. So it's improved quite a bit. Now, about 10 years ago, I updated the chart, and part of it was that the difficulty of using the charts was that people would take samples and they would classify the soil based on the sample. And the classification system is based on grain size, like for sands, like is it well graded, poorly graded, is it a sand or a silty sand, etc. And then based on Atterberg limits for clay. So was it a low plastic clay or a high plastic clay, etc. But that classification system is based on physical characteristics such as grain size and plasticity, not mechanical characteristics, which is what the cone is measuring. So when you push the cone in, the cone is responding to how strong and how stiff the soil is and what the effective stress is. And so it's a behavioral characteristic. That's why we refer to them as soil behavior type charts. It's not exactly the same as traditional classification systems that are very commonly used in geotechnical engineering. And so I updated the chart, and instead of saying sand, silt, and clay, I then started to use terms like, well, it's sand-like and it's clay-like, and if it's in the middle, we'll call it a transitional soil. And we also added that by putting a line across the chart, it said, well, if it fits above that line, it's going to be dilative at large strains. And if it plots below that line, it's going to be contractive at large strains. So now you've got descriptions that say sand-like and dilative, sand-like and contractive, clay-like and dilative, clay-like and contractive, and then clay-like and contractive, but highly sensitive. And then in the middle, you've got these transitional soils that can be dilative and contractive. So trying to get more of a behavioral type description. And the reason we want to know whether or not a soil is going to be dilative or contractive at large strains is that if you have a soil such as a clay, and it's going to be contractive at large strains, like a typical soft, normally to lightly over-consolidated clay, that if you shear it, it will have a tendency to contract. And that tendency to contract means it will develop positive pore pressures, and the undrained strength ends up being smaller than the drain strength. So if you know a soil is going to be contractive at large strains, you know that the undrained strength will be smaller than the drain strength. Of course, if it's dilative, you know that the drain strength is going to be smaller than the undrained strength. And so that immediately gives you a sense of what type of analysis you need to do, whether or not it needs to be drained or undrained, and what parameters you need to look for. And so that boundary of contractive dilative is based on soils that have little or no microstructure. And so in that publication in 2016, I added this plot on the right, which is the normalized cone resistance against what is the small strain shear modulus, which you get from the shear wave velocity. So G0 is the shear wave velocity squared times the mass density. And that's divided by the net cone resistance. So it's a sort of stiffness to strength ratio, which is a very common parameter in many theoretical solutions. So it's a rigidity index. It's a stiffness to strength ratio. And what we found is that when the normalized tip resistance is very high, this rigidity index is generally pretty low. And when the cone resistance is very low, the rigidity index is a little bit higher. In other words, the stiffness to strength ratio is a little bit higher. And so what we found is that most young, uncemented, ideal soils fell within a relatively narrow range. And the intercept of these lines gives this kg value of between 100 and 300. And so if your data with measured shear wave velocity fell within that bound, it said that the soils were basically well behaved, they were relatively young, and they were uncemented, had little or no bonding, and the mineralogy was relatively normal. It didn't have any unusual mineralogy. And so you would expect that most of the correlations would work quite well. And so the chart on the left would be considered to work pretty well. Now, if you had soil that was either very old, like in northern parts of Europe, where glaciation have created these sort of clay deposits that can be thousands of years old, millions of years old, so they're very stiff. Aging makes them much stiffer than they would be. So the shear wave velocity ends up being much larger than you would expect based on the tip resistance. So the data falls outside of that range. And so if it falls outside of that range, that's when we talk about that the soil has microstructure. So it's either cementation or bonding or aging. Those are the sort of primary things that cause microstructure, but also unusual mineralogy can cause it. And so if the soil has microstructure, then some of the correlations might not work quite so well. So that was a new addition to say it's important to identify microstructure. And then we added this chart in the middle that came out of the work by Schneider and Randolph and Paul Main. And that they looked at the excess pore pressure. So if you were pushing into a clay and you were developing excess pore pressures, then they developed a sort of a soil behavior type chart. But what I added to it was a dashed line that said, look, most ideal soils fall in the lower left-hand portion, but if it's got significant microstructure, it can start to plot way out on the right-hand side. And so what would happen is if you had a high normalized cone resistance, that would generally infer that you've got a heavily over-consolidated clay, and heavily over-consolidated clays are normally dilative at large strains. So you should expect to get a negative pore pressure from the cone. But if you measure a large positive pore pressure, then it says, well, hold on, we're expecting this to be stiff and heavily over-consolidated, but it's contractive at large strains. And that again, that's a sign of microstructure saying, yes, if you have like a cemented clay then it may appear to be very stiff because of the cementation. But if you shear it with a cone, you fail it by pushing the cone into it, then you break down the bonds and it actually contracts and you get large positive pore pressures. So that's the updated charts. They're becoming very popular and they're very useful. But to use them in their entirety, you do have to have shear wave velocity. So you've got to have tip, sleeve, pore pressure, and shear wave velocity. So I mentioned about how with digital data, there's been software development. And so about 15 years ago, when I was talking to companies and saying, are you using the CPT much and what are you using for? I started to realize that people were beginning to use the CPT more, but many of them were writing their own spreadsheets, which was problematic because they weren't quite sure how to do it correctly and they were making mistakes. And so I got into software development. And so I worked with a person in Greece, John Ioannidis, and he had a little software company called Geologis-Mickey. And together we developed this program called CPT. So it started off being called CPT-IT. And then he said, well, if I put that lowercase e in there, it actually spells the word CPT. And petite is French for small. And so it's like a small CPT program. And so I'll just show some examples. It's good for basic processing. So you can produce these nice plots very quickly. Basic measurements of tip, friction ratio, pore pressure, basic soil behavior type. And this is from a site in Venice. So it's interbedded sands and clays and silts from the lagoon in Venice. And here's the normalized plot. And you can see when you normalize, instead of the cone resistance, it's basically increasing linearly with depth in the clay-like soils. Now it's constant with depth and the sand layers jump out as being higher. And of course, the normalized pore pressure is 0 in the sand, and you've got a positive normalized pore pressure in the clay layers. And then this is the updated one. So instead of BQ, it uses U2. Same basic thing, a little bit more detail. So you can produce these plots very quickly. And of course, you can look at the data on the soil behavior type chart. So here on the right, they had shear wave velocity, and you can see that most of the data falls between this range. They are plotting a little bit towards the upper end. So although these sediments are quite young, they are plotting on the upper end of the range, which indicates there's just a little bit of microstructure. But we know from lots of research on natural soils that most soils have a little bit of microstructure, not enough that it influences the interpretation or the behavior in any significant way. So a lot of our traditional interpretation methods still work reasonably well, but it does indicate that, well, they're often a little bit stiffer than you think they are. But it falls within the bounds, so it says that the interpretation should work pretty well. And then the chart on the left is the traditional soil behavior type. And you can see that most of the fine-grained soils are contractive. The denser sand layers are dilative at large strains. So you can see the dilative sand layers and then some silty sands that are still sort of marginally dilative. And then the silts and then the clays are contractive. And some of the clays are actually getting into the sensitive region. And then the chart in the middle, the pore pressures are falling where you'd expect for a soil that has little or no microstructure. The boundary of microstructure was roughly here. So the normally consolidated clay has a positive pore pressure, and then the over-consolidated silts have some negative pore pressure. And of course, the sands have either 0 or negative pore pressures. So interpretation, one of the first things you often want to do when you sort of process the data, if I go back, let's go back to the raw data here. So when you're processing the data, one of the first things you want to do is you want to input where the water table is. Now here, of course, it's in the Venice Lagoon, so the water table is very close to the ground surface. That's visually clear from the site that you're doing the CPT. And they did a number of dissipation tests, and you notice that in the upper sand layer, the sand is quite free draining, and you can see it's pretty well hydrostatic. This blue line is the hydrostatic line with the water table half a meter down. And you can see that every time it hits a sand layer, it basically goes to hydrostatic. And the deeper sand layers that are quite dense, they're actually generating slightly negative of hydrostatic. It's still a positive pore pressure, but slightly negative of hydrostatic. And all of the clay layers are developing positive pore pressures. So you can interpret a wide range of parameters. You could estimate the permeability based on soil behavior type chart. So it just basically takes the soil behavior type chart, and if it's a sand, it assigns a high permeability. If it's a clay, it's a low permeability. And there's quite a lot of historical precedent to guide how that varies, and it actually varies as a function of IC. So you get a continuous profile of the variation in permeability, and it covers 10 orders of magnitude here at the bottom. So each one of these um, lines here is 3 orders of magnitude. And then, of course, countries that use the SPT, they still like to see what the equivalent N value is. So you get a profile of N, but not just N, it's N60. It's the N value at 60% energy. And then the next 3 plots, which are designed for sand-like soils only, is the Young's modulus, relative density, and peak friction angle using well-established correlations. And you can see that the soil is in fact quite variable, and you can see that it's only showing the data in the sand layer. So it shows a bit of a tail, because when the cone is just entering a sand layer, the cone tip is just increasing as it enters the sand layer. So you get this little bit of a tail, and you need to just ignore the tail and take the endpoints. And then you can estimate the one-dimensional constrained modulus, which is commonly used for settlement calculations in Europe. The next one is the small strain shear modulus. So assuming the soil is young and uncemented, it says where you can estimate the small strain shear modulus. Then the next plot is undrained strength. The black line is estimating the peak undrained strength with a cone factor. At the bottom here, it says the cone factor was assumed to be 14. And then the red line is the remolded undrained strength, which you get directly from the sleeve friction. So you can see that these clays have some level of sensitivity, like a sensitivity of about 3, which is relatively common. A lot of clays have a little bit of sensitivity. It's only certain soils are completely insensitive. Then the next plot is just the unstrained strength ratio, and it shows that there's a little bit of over consolidation near the surface, so the undrained strength ratio is a little bit high, and then as you go deeper, it begins to drop down to the typical values of an undrained strength ratio of about 0.2 to 0.3. And then the last plot is the over consolidation ratio, sometimes referred to as the yield stress ratio, but commonly the OCR. And you can see that the OCR near the surface is around 2 to 3, and then it drops down to 1 at depth. And the software that we developed also has an ability to run statistics on any of these parameters. So for example, if you want to know how the undrained shear strength ratio varies in one of these clay layers, then you can just identify the clay layer, like maybe from 8 meters down to 16 meters, and ask it to run the statistics. So on the left is a frequency distribution showing the mean and standard deviation, and then the plot on the right shows the cumulative distribution. So the nice thing about running statistics on a given parameter is, rather than just selecting the mean value, you get a sense of what the standard deviation is. So how variable is the soil? And so depending on the type of project, are you going to select a value that represents the mean, such as the 50% value, or do you want to take something like the mean minus one's standard deviation, something around the 20th percentile or the 80th percentile? So depending on the type of project you're working on, whether or not going low or high is conservative or not, you can do that. And the program allows you to do that on individual parameters in an individual profile, and also to actually look at the statistics of the same layer across multiple profiles. So let's say you did 5 CPTs and you identified the same clay layer in all 5 CPTs, then the program will actually run the statistics for all 5 of the CPTs on that one layer. And then also you can, if you've got the measured shear wave velocity, so the measured shear wave velocity here is shown in red, and the black one is the estimated shear wave velocity based on a young, uncemented soil. You can see the two agree very well, so shows the correlation is pretty good, and that the soil is essentially young and uncemented. The middle one is state parameter, which is sort of critical state for sands, and then estimating K naught, estimating sensitivity, which, as I said, was on average about 3. And then the last plot is sort of a correlation that came out of Norway, where you could try and estimate the peak friction angle in a clay from the undrained comb penetration using the pore pressure as a way of adjusting the interpretation. And then uh, because you have to normalize the data, you have to calculate the overburden pressure and the effective overburden pressure. So you need the unit weight. So the program allows you to just put in a single unit weight, typical value, maybe 18 kilonewtons per cubic meter, and you can vary it to see how sensitive the results are. But about 15 years ago, we developed a correlation that said, well, you can actually estimate the unit weight based on the soil behavior type. So the non-normalized soil behavior type chart, you could estimate unit weight. And so we added this to the program. So here's a plot of the estimated unit weight. And you can see on average, it is about 18 at this particular site. But of course, it's lower near the surface and gets higher as you go deeper. So of course, as it gets denser, the unit weight increases with depth. And it turns out this is actually quite useful. And so a group in New Zealand said that they were using this, and below the water table, they would then estimate the water content and void ratio based on standard relationships between specific gravity and total unit weight for saturated soil. So you could estimate the water content. And so if you've got clay-like soils and you take a number of samples, then the simplest thing to do with your sample is to take a water content. So if you measure the water content in your samples, you can overlay that over the top of the estimated water content and see how well your estimate of unit weight is. And of course, also get a measure of what the void ratio is and see how well your estimate of void ratio is. And then you can get dry density. And on the right here is plasticity index. There's a number of correlations. This is one of the newer ones that sort of estimates the plasticity of the soil. And you can see that in the sand, it's essentially non-plastic. And in the clay, it says it's on average of about a PI of about 20, which for this site is actually pretty close to what it is. And I mentioned about dissipation tests. So as I said, you can do a dissipation test. So here's the measured pore pressure versus logarithm of time. And so you get this sort of theoretical dissipation. And if you want to get T50, what you do is here, the initial pore pressure was a little 829 kPa, and U0 was estimated to be about 37 kPa. So halfway between the two is 433. So you come across, and that works out to be 7 minutes. So T50 is 7 minutes. And so you can get T50, and that can then be used to estimate the coefficient of consolidation and permeability quite accurately. And of course, U0 tells you if it's hydrostatic. Now, in a sand soil, this would be much, much faster, and you would reach U0 in typically less than a minute. And so, T50 might be, a couple of seconds, and then T100 would be maybe a minute, and you could get the piezometric profile. When it comes to applications, in the early days, a lot of it was deep foundation, pile design. Then shallow foundations became popular, estimating the bearing capacity and settlement. Of course, liquefaction analysis. So in the mid 1990s, we developed a method to estimate the liquefaction triggering, and over the years, it's developed. And so we actually developed a sister program called SLICS, or CLIC, which is a CPT-based liquefaction program that allows you to do detailed liquefaction analysis. And in fact, I have a webinar coming up on April 1st where we're going to demonstrate that software. So on California time, it's going to be midday, which unfortunately for you means it would be midnight. And then for quality control, for ground improvement, and for environmental, lots of applications. I'll just illustrate a few. One of them is foundation design. So the software has a little bearing capacity module where you just click on it, put a range of footing widths, and it'll estimate the ultimate bearing capacity. And of course, you then divide that by some factor of safety to get sort of an allowable bearing capacity. And then with that allowable bearing capacity, you could then do a settlement calculation. So you take the one-dimensional constraint modulus and the OCR, and you do a settlement calculation, and it plots out not just the settlement, but the profile of settlement with depth. And you can add in a little bit of creep if you want to for rate effects. So if if you want to know, well, how much extra settlement could I get for creep, it'll add that on using a correlation from Mesri, which is pretty effective. And in fact, at this Venice site, it actually got a very good answer. They did a full-scale loaded tank at the site, and they measured the primary and also secondary consolidation. And the software based on the CPT actually got a pretty good answer. It was pretty close to the right answer. So it's actually surprisingly good. And then for pile design, there's a little module. It's very simplified, but you put in the details about the pile, what type of pile it is, whether it's driven or bored, what type of driven pile it is, etc. And then it'll calculate. The red line is the allowable, with all the factors of safety applied. So the red line is the allowable shaft resistance or the sleeve resistance. And then the blue line is when you add on the base resistance. And so the blue line is the total. And when often you find long, slender piles, it's dominated by the shaft resistance. And then also there's a little feature where you can also estimate what the load settlement curve of a single pile is based on some assumptions of how much relative displacement is required to mobilize it. So that's a very quick overview of the history of CPT and interpretation and geotechnical applications. There's also a wide range of modules for environmental. I won't go into a lot of detail, but the common ones are the membrane interface probe. That's a little device that has a heater on it, and it causes the gases to vaporize and pass through a membrane, and then you can run chemical analysis on the vapor. And so it's referred to as a membrane interface probe, and it's very useful for detecting different types of contaminant in the ground. And then there's a hydraulic profiling tool. So instead of measuring the pore pressure in saturated soil, what it does is it actually injects water out at a slow, constant rate and measures the pressure required to inject that water out. So in sands, of course, the pressure is very low, and in clay, the pressure is very high. And so that can be used to estimate the permeability of soils, particularly above the water table. So if you've got deep water table, but you still like to know the permeability, of course, the standard cone with pore pressure measurements doesn't work very well, because if you're above the water table, you're not measuring any pore pressures. Whereas this device sort of forces the issue and injects water out. So it's becoming quite popular. And then for petrochemical type contaminants like fuel and oil and gasoline, etc., there's this ultraviolet induced fluorescence. So it shines an ultraviolet light out the side of the cone and measures the fluorescence. And the type of fluorescence you get back will tell you what type of hydrocarbon is in the ground. And then, of course, I also mentioned about measuring the electrical resistance or conductivity, and that can be used if there are heavy metals in the pore fluid, or if the water is salty or fresh. And so the electrical conductivity is very different between fresh water and salt water, and so it's used to identify saltwater infringement into groundwater areas. So these modules have become very popular. Here's just an example from one push. So this has got the standard CPT data here. It's just showing the tip and pore pressure. Water table is down around 9 meters. And then the next plot is electrical conductivity. The next plot is the pore pressure from hydraulic profiling. So you can see in the sands, the pore pressure is low, but in the clay, it's high. And then from that, you can estimate permeability. So instead of doing individual dissipation tests, where maybe you might do 5 or 6 dissipation tests, here you get a continuous profile of permeability from that pore pressure. And then the last 3 plots are from the MIP. So it's measuring different contaminants. I can't remember exactly what these acronyms stand for, but they're measuring different chemical constituents in usually the pore fluid. And of course, I talked about soil sampling, but there's also water and vapor sampling is popular in the environmental area. So what they typically do, push the CPT, get the profile, determine where the water table is, and then if you were worried about the water being contaminated, you would move over, push one of these water samplers down, and then you expose the little filter element, and then you can draw water in and measure the contamination of the water. Very popular. And of course, you can also install standpipe piezometers as well as vibrating wire piezometers with CPT data. So you can do a lot. Now, I've covered the ground quite rapidly there. So in summary, lots of progress has been made in the last 50 years. Cones have become more reliable, more robust, more sensitive. They're digital, lots of added sensors. The digital data collection means that processing and interpretation and plotting the data have become much easier. Wide range of pushing equipment. So now it's possible to push with lots of reaction, even if it's lightweight equipment. So relatively small equipment can be anchored down and you can push into pretty hard ground. I was at a site just 2 weeks ago, and it was in an area with residual soils. And so they were using a large dozer, and they had attached a portable CPT hydraulic unit to the back of the dozer, and they were pushing into fairly stiff residual soils, and they were pushing over 30 meters with a 20-ton reaction from the dozer. Improved interpretation supported by theory, many applications, and increased case history database, lots of case histories. And the test now is pretty well the most popular in situ test in most parts of the world. Because of its efficiency, the fact that you get a continuous profile of data, you get multiple measurements in one sounding, and it's cost effective. So it's rapid, it's inexpensive. So it's becoming the most popular in situ test in the world, at least in soils where you can push the cone. Now, obviously, if you've got an area that's bedrock, hard rock, you're not going to push the cone. You can push the cone into soft rock, like these residual soils, or here in Southern California, we have relatively soft sandstones and siltstones, and we can push the CPT into it. So you can push it into pretty hard ground. If you've got really dense gravels, it doesn't work there. So future, we're going to see continued improvements, continued trend towards continuous pushing, although that's only in specific applications, particularly offshore. The likely growth in combined drilling of things like sonic and CPT, we're going to see a lot of growth there. We're going to see some development in wireline. There are a number of people have done wireline CPT to push CPT much deeper. If you're pushing CPT from the surface, once you get to about 100 meters, it gets pretty hard to push deeper. You get rod friction, even in soft soils. Yeah, you get rod friction. It's quite difficult to push beyond 100 meters. It is possible, but it's generally quite difficult. And it's time consuming. And so in the offshore, they have done wireline CPT, and that's been scaled down. So if you need to do very deep CPT, or you need to go through hard ground to get to softer ground, then wireline CPT is also being used. So future progress, more sensors are being developed, advances with surface geophysics, and now it's common to do things like MASW to get two-dimensional shear wave velocity profiles, identify where the softer regions are, and then go and do seismic CPT that verifies the shear wave velocity and also does the testing in the areas where it's most needed. And then, of course, advances in push-in samplers, including undisturbed samples in softer soils. Continued growth in documented case histories, as more and more people use the CPT and as case histories occur, the number of published case histories continues to grow. Increased use of software, and of course, increased use of big data. So things like liquefaction analysis, the fact that we have now over 30,000 CPTs in Christchurch. One of the futures may be that in the future, you'll have your CPT profile. You might submit it to a database. The database will search for sites that have very similar cone profiles, and then come back and say, we found a number of sites that match your profile, and at these sites, this is how they behaved under certain conditions. So under certain earthquake conditions or under certain loading conditions, this is the way they perform. So you would still do your standard interpretation, but you could then compare with the database to say, well, my interpretation said this would happen, but the database said it was slightly different. So that will account for the natural variability of real soils. So almost everything I've said is contained in a free CPT guide. So it's on the seventh edition now. And so you can download this from either my website or from Geologist Mickey's website. And all of my websites, they're on the Greg Drilling website, but they're also on a YouTube channel that I put together that compiles all of them. And so you can link a lot of webinars I've done in the past. So if you want a little bit more detail on anything I've talked about, you'll find a webinar that will cover that. And so at your own time, you can watch it for free on YouTube. And you can also download this guide. So nearly everything I've talked about is in that guide, and it's really quite helpful. So I'm happy to take any questions if we have time. Thank you.
Thank you so much, sir, for such a comprehensive coverage of CPT in just about 1 hour. You have given a very glimpse of the primitive CPT to most advanced CPT, including the instrumentation, its applications to a general stratigraphy to seismic hazard, geohazard, as well as for geo-environmental applications. Thank you very much for your comprehensive coverage. And I would like to update you that in India now, in less than a month, we are pushing for a code on ECPT, electronic cone penetration test. So far, it is an analog is there. I'm one of the panel member for that codal provision, along with Sri Sanjay Gupta is the chairman. And day after tomorrow, we are having a meeting on BIS before that. So
Good.
thank you so
Good.
much. Thank you so much, sir.
You're
I would
welcome.
like,
Thanks, everyone.
thanks. We'll take a few questions. Just a minute. One of the participants, Dr. Prasanna, is asking about the question: how can we find undrained residue or post liquefaction shear strength from CPT data? Any references, please?
So I think the question was, how can we estimate the undrained strength for flow liquefaction from drained CPT data? Is that what the question was?
Yeah, it is what how can we find the undrained residual shear strength post liquefaction
Yeah.
using CPT?
Yeah, well, I updated my publication. So I published a paper in the Canadian Geotechnical Journal in 2022. So 4 years ago, there's a paper in the Canadian Geotechnical Journal. I can share a copy with you, or you can get it from my website. So if you go to CPT Robertson, my website, you'll see you can download a copy there. So I provide all the details there. So basically what it says is that we looked at case histories and we developed a correlation between the CPT in sand soils, which of course is a drain penetration in sand, and how to predict post-earthquake undrained strength. And so that's basically done through relative density state parameter type correlations. And that's well published. And then we also identified that in sort of silts or clay-like soils, or low plastic clays, that can also suffer undrained strength loss, is that because the cone penetration is already undrained, then you can estimate it directly from the sleeve friction. So in silts or in low plastic clays, if the cone penetration is undrained, you just get it directly from the sleeve resistance. But in sands where the penetration is drained, you get it through an empirical correlation that's supported primarily by case histories. And it's also summarized in the CPT guide.
Dr. Prasanna, I hope that clarifies for you. We have a couple of more questions from another participants. Whether negative pore pressure are due to over consolidated clay or dense sand or due to unsaturated filtering.
Well, it can be any one of those. So if you do dissipation tests and you determine the equilibrium pore pressure, and of course, if it's hydrostatic, you extend it to get the groundwater. But even if it's not hydrostatic, there might be downward flow or there might be artesian upward flow. If you do enough dissipation tests, you can extrapolate it to where the piezometric surface is. So if you're below the water table, you know it's not due to partial saturation. So then the issue is simply, is it an over-consolidated clay or is it a dense sand? And of course, the basic cone data will tell you that. So if it's got a high tip resistance and a low friction ratio, it's a dense sand. And so if you're getting negative pore pressures in a dense sand, that usually means it's a dense silty sand. It means that it's got enough fines that it's not free draining. And so it's a dense silty sand and you're getting slightly negative pore pressures. If it's an over-consolidated clay, then you'll have a high normalized tip resistance, but you'll have a high friction ratio. So now it will plot on the right-hand side of the chart and it'll plot high up, meaning it's an over-consolidated clay. And of course, you're getting these negative pore pressures because at large strains, it has a tendency to dilate. And so you get these pore pressures that are negative of equilibrium.
This is also my question. Next question is also is what I wanted to ask. How to incorporate suction of unsaturated soils in SBT charts? And also the
Yeah.
associated friction angle due to suction when a cone is pushed through unsaturated soils.
Yeah. Usually the role of suction is not as big as people think it is. And it's for two reasons. One is that suctions in sands, of course, are very small. In silts, they're relatively small, and in clays, they can be very large. But clays tend to have a high air entry value, so they tend not to desaturate very well. So plastic clays tend to remain almost saturated, so the suctions are not as high as you think they are. So the problem areas are in the silty soils, where they can be unsaturated and the suctions can be moderately high, maybe 1 or 200 kPa. And so what happens is that the cone resistance, of course, increases with overburden pressure. So it's only a problem at relatively shallow depths. So maybe in the upper 5, maybe as much as 10 meters. So in the upper 5 meters, suctions play a bit of a role because the overburden pressure is not that high, maybe less than 100 kPa, but you could have suctions of 100 kPa. And you can correct for it. But it's not simply correcting for the effective stress to say, well, if I've got an overburden pressure of, say, 50 kPa and my estimate of suction is 100 kPa, then it's equivalent to 150 kPa because it doesn't quite work that way. Because when you look at the research on the effect of suction is not one-to-one with strength. So if you increase suction by 100 kPa, the shear strength does not go up 100 kPa. So the friction angle in the direction of suction is not the same as the friction angle in the direction of effective stress. So let's say you have a silt. Let's say the friction angle is 30 degrees. So the traditional strength envelope of shear stress against effective confining pressure would be 30 degrees. But in the direction of suction, the slope only goes up at typically about 10 degrees. So the strength only increases a little bit with that suction. So the effect is not as big as people generally think it is. So in general, the effect is not that big. However, people have shown that in areas where they get large seasonal variation between a wet and a dry season, so the water table can fluctuate. So the water table can come up and it can be saturated, and then in the dry season it drops and it becomes unsaturated, and the upper soils might be relatively fine-grained, so they develop relatively large suctions. So you can get a change in the tip resistance, but you don't get changes of like 2 or 3 times. Often at the worst, it might be twice as high, but generally it's maybe 50% higher. So that there is an effect of suction. And people have shown that if, of course, you measure where the water table is, if you can make an estimate of the suction, and there's various ways to do it. One is that if you have a saturated porous element, it will measure negative pore pressures, at least down to about 100 kPa. So if the suctions are quite small, the cone will actually measure the small suctions, but of course, small suctions don't have much of an effect. It's the big suctions that have an effect. And so you can tell that that's a problem because the cone tends to desaturate. It gets to negative pore pressures and they bottom out at about 100 kPa because at 100 kPa, air bubbles come out of solution and the cone desaturates. So that's a warning that the suctions are quite high. But if you take samples and measure the moisture content, and if you run a soil water characteristic test in the lab, or you estimate it based on the characteristics and Atterberg limits of the soil, then you can estimate the soil water characteristic curve. And so from the moisture content, you can estimate the suction. And then from that estimated suction, you can then estimate what the effect on the tip resistance. So you can correct for it. But typically, it only plays a role in shallow data. So if you have like shallow foundations, and you're worried that you did the CPT in the dry season and you're worried about the design of the shallow foundations for the wet season, well, there's two approaches. One is, well, do the CPT in the wet season would be the preferred way because that's going to give you the lowest answer. But if you can't do that and you can only do it at one time, and so you want to correct for it, then there is a way of correcting for it. For bigger projects, like mine tailings that I do in where the structures are much larger, so we go much deeper and the overburden gets quite a bit higher. And so suctions play a much smaller role in those situations. So it's only an issue for shallow foundations in regions that have big difference between wet and dry season, such as India. There are parts of India that have big difference between wet and dry season. And so if you run the CPT in the dry season, it may be giving you a cone profile that's higher than what it would be in the wet season. And there is a way of correcting for it. And probably the easiest one is to simply take a couple of samples, move over, push in one of these sampler devices, take a few samples, measure the moisture contents, determine the Atterberg limits and grain size, and then estimate what the suction is based on estimated soil water characteristic curves. And then there's a technique for adjusting the tip resistance based on the suction. There's a couple of publications on that.
Yes, sir. Thank you. I request Sanjay Gupta, sir, you can provide a few remarks on our upcoming code.
Okay. Thank you, Janki. Am I audible? Namaskar.
Yeah, you are audible.
Well, Professor Robertson, as I always say, I think maybe I have heard you a number of times, but each time gives me an inspiration to come out with something new, especially to add into the Indian scenario. Well, as we have been rather working for the last few years onto the new BIS code, onto our electric code penetration test, for the piezo cone. Now, by the time, we come out with the first, the version of it, we come to know about the seismic code. Now we want to add that. So it is a never-ending process. Well, all the same, day after tomorrow, we are going to have a meeting. And I'm quite hopeful that in the BIS sectional committee, we can discuss. And shortly within 2026 itself, we should have a first code or practice onto this. In India, we have been doing a lot of CPTs. And well, the results are really, really amazing. We are very happy about it. And each site, each test gives us something new to learn, as you have just mentioned. And what I would say is that we are going to have so much of a database that with all the webinars and all your publications, we are able to understand the soil and the site conditions in a much better way. We hope to have your blessings, as always, on our CPT journey in India. Thank you. Namaskar.
Thank you, sir. I know it's Robertson, sir, you're muted.
Yeah, thank you for that. Yeah, I look forward to seeing the growth of CPT in India. As you're growing economically, and of course the need for more advanced data and more advanced construction, it's really good to see that you're going to be doing more CPT. And I think, as he said, you'll find that the more you do it, the more you're going to enjoy the data with the level of detail it provides about the ground. So I look forward to your growing experience.
Thank you.
Thank you,
I know.
boss. And
Thank you.
in fact, you have been a lot of inspiration, and my team had been interacting with you, talking to you each and every time we get stuck with some data. And you have been of a great help in understanding and improving the whole version in our country, in India. In that one, Saurabh Gupta and Abhishek, they also join me in really thanking you from our hearts.
You're most welcome. Thank you.
You, sir. I know it's already 11 o'clock for you in the night. So thank you so much. All the
Yeah,
questions, I will forward it to you in the chat box for your request. Sir. Thank you so much, sir. It's already dinner time for you. I'm sorry. Thank you so
yeah.
much.
And I shared, you have a copy of the slide, so you're free
Yes.
to share that.
Thank you so
Right,
much.
sir.
Thank you.
Thank you, sir.
Take care.
Thank you.
Bye.
Thank
Thank
you, sir.
you. Bye bye.